My name is Scott Stetzer. I'm the Vice President, about to fall over here, for KIOXIA America. But today I'm not speaking to you from my day job at KIOXIA. I'm speaking to you on behalf of an open source project with the Linux Foundation called Software-Enabled Flash. Okay, so Software-Enabled Flash. Software-defined has actually been doing a great job of changing how the compute world, especially in the data center, works. I think the biggest success story in terms of software-defined has been software-defined networking. We used to be hardware-bound on networking, routing, and switching. And then it became software-defined. The computer became the router. Phenomenal what you can do with routing network packets today. Just amazing. What we'd like to do is bring that forward and do the same thing with Flash itself. Now, Flash is different from hard drive technology. Hard drive technology is our storage paradigm for today. It's been around since the mid-'80s. And even today, block mode access for storage is still cylinder head sector based in terms of its traditions. Flash works differently. Now, when we first deployed Flash, it was a faster HDD. And it was important that it worked like an HDD so it could plug and play with the existing storage paradigm. But today, we don't need to stick with those paradigms. We can bring Flash forward and we can use every aspect and capability that Flash has available to you that's not being utilized today by changing it to a software-defined paradigm. The key to this is, for data centers and for applications developers, control over your latencies, control over your I/O, and control over your data placement, isolating workloads from each other. A real tremendous advantage that I'll talk through here in a moment. So, how many people here are storage developers? It's an important feature set. The technology for software-defined Flash was developed by software guys, storage software guys. As a matter of fact, the architect of that is sitting here in the room, so I'll leave everybody to guess who the architect here is. But the origins of this was from the software perspective, not the hardware perspective. So how do we define and deliver these capabilities for you, the developer, the software developer? It's hardware and software working together. You can isolate your workloads. You can isolate your tenants. You get complete and discrete control over data placement at the hardware layer down to the flash die. You get some incredible queuing capabilities. There are 3 different queuing engines built into the API and into the hardware, and I'll show those to you later. Latency is the #1 aspect that everybody says, I want control over latency in their storage deployments. You get full control over how and when any background activities occur within the device through the API. And you'll hear this over and over again today. All of the source codes for how this is deployed in different drivers and in the libraries is all going to be made available to you through the open source project. So innovation at the speed of open source. It's a very key aspect. It's today already an open source project, softwareenabledflash.org. It's hosted by the Linux Foundation. We're using the BSD 3-clause license for both the API and the SDK. Now, the BSD 3 clause is the most permissive license that you could possibly have that we're aware of today for open source. And we're using that to make sure you guys can do whatever you need to with the code, use it, modify it, change it, make it work for you. And with any luck, maybe you'll contribute some interesting code back to the project. We know you need multiple vendors. From the beginning, the API was designed as an open source ecosystem to enable multiple vendors. As a matter of fact, even today, we're talking to 2 other Flash vendors about joining the project. One of them's actually in the process of doing the registration for becoming a member. What does this mean to you in terms of a value proposition? If you can pick up a software-defined Flash drive hardware from your favorite vendor, deploy your software, you get a faster time to market, faster than going out and designing and building the drive from scratch yourself. And of course, the benefit here is, how do you improve your deployments? How do you get there faster? So I think I mentioned this already. We're designed to be vendor neutral as a project. All Flash vendors are welcome. All controller vendors are welcome. It's managed under the Linux Foundation. All the governance committees and all of the management functions are set up. All of the real activity with the project happens within the Technical Steering Committee. Technical Steering Committee meetings are open. They're free. You do not have to be a member to join and call into those. The next Technical Steering Committee meeting is going to be held in November. So that's coming up very soon. If you want to join that, the best way to find out about it, go to the project website, sign up for the mailing list, and you'll get all the notifications about the TSC meetings and the release of new code. The API is already available and out on GitHub today. The SDK is coming soon, and again, the SDK will include all of the source code for all of the different drivers and libraries. So what does this mean to you, the developer? I know I saw at least one person raise their hands. There are tools and value propositions that make a lot of sense going software defined. Developers are all about how do I control my I/O, how do I control my storage? So the key ones here, of course, isolation. How do I get myself isolated from noisy neighbors? One person's I/O stepping on somebody else's I/O. How do I manage data placement so I can control that isolation, either by tenants or by workloads? Latency outcomes, the number one thing all of the big guys, the hyperscalers have been talking about, I need to control my latencies. And that doesn't mean one solution. You may want the highest I/O, or you may want consistent I/O with no outliers. The nice thing about being software defined, you can go in and set programmatically how you want those latencies to occur. You've got complete control over how that happens, and you can change it on the fly. Also, built into the hardware side of this, on the controller side, are a number of accelerators, hardware accelerators. One of them is a copy offload engine. This simplifies the task of doing routine application work by transferring a lot of the muscle that's necessary to do that down to the local controller inside the device. One of those would be, for example, with a traditional SSD, you need to do garbage collection. You can give that back to the device so the host CPU does not have to do that work. Another interesting aspect, one of the things you can do with software defined for flash that you can't do with a standard SSD is run multiple protocols. So a traditional SSD runs a block protocol. Remember the legacy HDD paradigm of cylinder head sector? That's block mode. Today it's run as LBAs, but we have a driver built to run block mode as an example. Again, that's in the SDK. The source codes will be available. We also have an example driver for zone namespace, ZNS. We have a sample driver for smart FTL, and there are others that are in the works too, like an object storage layer. Now, all of these protocols are software drivers. Plug them into the host, all of a sudden your software-enabled flash drive is working like a block drive. Change the driver, works like a zone namespace drive. Change the driver again, you've got a smart FTL drive from one piece of hardware. Where else can you go buy a single drive and run any protocol that you want without changing or going and buying a new drive? The other really useful function of this, since it's software driven, virtualize the device. Now you can run that block protocol next to that zone namespace protocol and that software smart FTL protocol and run them all simultaneously on the same block of storage. A very powerful feature from being software defined. So what does this mean, right? Faster deployment. How do you get to spinning up your applications faster? How do you get to redefining and redeploying applications when you need to move workloads around? The key to this is abstracting the flash from the hardware from the software. That abstraction allows you to do several things. One is you can run multiple vendors without having to change the software layer at all. The other one is simplifying your migration to the next generation of flash. We are currently doing the development work on both TLC and QLC media. Through that abstraction layer, the software doesn't change whatsoever. The vendor of the flash device is delivering you the best white box software-enabled flash SSD that works with any of the upper layer software. No changes required to the software. So the solution really does become hardware and software working together. You've got flash behind a controller with a very small firmware layer that implements the API in hardware. That means each flash vendor can design that storage device to be the best they can possibly be for their particular flash type. The controller has a small DMA engine for the I/O, generation-specific logic for whether it's TLC or QLC or PLC, whatever comes next. ECC built in, you've got a DRAM controller in there, and then the flash. So one person's flash versus another person's flash can easily be mixed and matched at a per device level. The software side is where it becomes very interesting because, again, the abstraction allows you to implement different hardware vendors all using the same host-level application software. So the hardware, again, vendor configurable. Each of the flash vendors can deliver their best flash capability through the API. Form factors, flash interface protocols don't really matter. They can be designed in and delivered to you based on your requirements. Think about it again like a white box flash device. If you've built your own drives, you don't have to build anymore. You can buy this white box drive and implement your software. On the hardware side, there's also a number of accelerators built in. For latency control, there's 3 different hardware-based queuing engines built into the controller. A simple priority queue. There's a nice, easy round-robin queue, first in, first out in terms of all of the queue for the I/O. And there's a very powerful weighted die time weighted for queuing control that allows you full, tight control over each individual I/O. In each case, you can set up policies for each of these engines, runs through each of the 8 queues. But with the die time weighted fair queuing, once the policy's in place, if you get a priority I/O coming in, a read or write request, you can change the weights for read and write I/O, and that particular I/O will be serviced according to that new priority that you've assigned it. And this is all programmatic and can be done on the fly. Another feature built into the hardware is that copy offload feature. Now you would think about this primarily from the aspect of doing garbage collection inside of a traditional SSD. It's an important aspect. And under program control, you can kick that off or delay kicking that off so it doesn't interfere with your I/O and your workload. But think about what you can do with copy offload aside from doing garbage collection at the device layer. Databases. You've got database compaction that needs to happen. Make this very efficient. Let the device manage compacting your database, picking up the data you need to keep, moving it to a new location, and the drive will tell you where he stored that data. Log structured databases for merge trees. Range copies for object storage. And of course, back to garbage collection for a standard SSD style device. So at this point, the hardware becomes that physical layer. You can go in and you can define from that physical layer what we would call a virtual device. That is, take individual flash die, group them together, and create what we would then call a virtual device. That virtual device is then exposed to the software side of things, and you get a quality of service domain in the software layer. This is where you can do that workload isolation. The flash die are isolated from each other, and then inside that quality of service domain, you can have multiple quality of service domains within a virtual device. And each quality of service domain can be isolated as well. So think about it. You can run per workload, per quality of service domain, your own separate superblock arrangements, your own separate garbage collection within that software-defined quality of service domain. Garbage collection can happen inside there. And while it's not mentioned here, you can also apply your own security protocols within a quality of service domain, completely separate from that other quality of service domain that's running a different workload. So the software stack becomes ultimately customizable. Again, it's software. Pick up the example code, change them as you need them, or use them as is, right? The software stack chooses the level of abstraction you're going to use. You can leverage the work of, it's open source, so hopefully the community is supporting each other by giving good code examples. I really do expect that we're going to see use cases for software-enabled flash, software-defined flash, that I can't even dream up looking at the project from where we're at today, right? It's built for customization. Pick up the source code, look at how it's implemented, see how you can apply it to your own code, grab the drivers, modify them as you need them, and use them to your purposes. Again, all of the source code is going to be made available as part of the SDK. Traditional storage stack, storage application goes through the kernel, through the file system, through the NVMe driver, and down to the device firmware. Now, the SCF API and the software development kit can route through that through a standard block I/O protocol. Or that storage application, the application itself, can bypass that entire stack and go right down to the device and write directly to the flash itself without having to go through the operating system storage stack. So what do you get when we bring to you software-defined flash? From the OSS side, we talked about the hardware already. Talk about the software a little bit. The API is the important aspect of this. This defines how everything works, right? It's an application programmer interface. The low-level wrapper of all of the commands that are going to work for you, the developer, defines how everything works. And it's built, again, to be multi-vendor capable. We've got multiple sources that we're going to be bringing forward for this. In addition to the API is the software development kit. We all know the software development kit is your tools or your window into how to actually implement this with your own programming projects. It's C language based. We also have Rust drivers. There's a Python driver for it. It's fully enabled for both 32-bit and 64-bit architectures. We're using the most modern Linux kernel available. I think I mentioned we're open source. We're part of Linux Foundation, so of course we're using the latest kernel. That's very important for some of the features built into the API as well. The libraries are both shared or static, depending on your requirements. Callbacks are event-driven. It's thread-safe, completely lockless, and modular. And by modular, sorry, I thought the hold that thought on modular for a moment. Source code, I think I've said this before. The source code is available. Have I told anybody that we're going to make source code available? The API and headers is that thin provisioning layer defining how you access the device, right? The software development kit includes an FTL, a fully user-level example FTL, all of the virtualized device drivers. There's a patch to FIO in the software development kit. This is important because FIO is the tool we all use for testing storage devices. So you can actually pick up a software-enabled flash device, use the FIO tool, and start testing without actually having to write a single line of code. There's also a CLI, command line interface tool, that helps you and does the definition and setup of the virtual devices, the QoS domains, and setting the policies for I/O. That also will include all the source code, so you can see how to implement and turn on and off all of these commands through that. So the FTL, the modular FTL, the key to this is modularity according to our architects. The ability to pick up this FTL and use portions of it, see how each portion of the FTL is implemented in source code, and use that FTL either in its entirety or in certain pieces of the FTL itself. And again, full documentation of all of these capabilities are there. I'm actually amazed at the level of documentation our team has put together in support of this project. Virtualization. So we use the Virt.io driver as part of the code base. We also implement through QEMU. Remember I was talking about how we can run multiple protocols virtualized on a single device? That's done through QEMU in this QEMU driver. And again, full source code's available. We've got traditional block mode capabilities, zone namespace capabilities, smart FTL capabilities, and we're looking at a few additional drivers as well. All with discrete control over latencies, data placement, and queuing controls. So let me show you a quick demo of all of this in action. You can see that, I'm going to go in and stop this real quick. So let me talk you through what you're seeing. This is a heat map of I/O onto a single SCF device, a single drive. You can see 32 die put up on the chart. And you can see 3 workloads running. One is a 100% write workload in red bars. In the middle is a mixed read-write workload running. And on the right-hand side is a 100% read workload running. The key to the heat map is showing you that physical hardware isolation. Notice that there are unused die between each of the workloads. That's not because we don't want to use the flash die, it's because we wanted to make it very obvious that the workloads are completely isolated from each other in the hardware. Oops, now I'm hitting the wrong buttons. And let's get this going again. So you can see I/O is happening on this device on 3 different workloads in 3 different I/O mechanisms, completely isolated from each other. Now let's turn off one of those workloads, and you see the other 2 workloads keep running, no change in their impact, no change in their performance. Turn off another one, same thing happens. Complete isolation. If we turn around and start turning them on again, you can see as we add workloads, completely isolated by hardware, again, no impact to the neighbor's workload. That noisy neighbor problem is now completely solved at the hardware layer, simply by isolating die from each other. So, as I wind down my discussion here, software-enabled flash, as an open source project, needs you, the developer, to join and be part of the project. Again, I think there's going to be applications use cases for software-defined accessing flash that I can't even dream up today. I'm expecting to see some really phenomenal and fantastic applications come out as part of this project as it moves forward. The location to get information is on the page here, softwareenabledflash.org. The call to action, first and foremost, if you've got questions, since I've used up pretty much all my time, there's not a lot of time for Q&A, I apologize. But come by, talk to our team at the booth. I'll go over to the booth. I'll stand by the doorway if that helps. The TSC is where all of the key activity happens, where all the announcements are going to be coming from. So go to the website, go to the project, sign up for the mailing list, and come to the TSC meeting, see what's happening, see who the other vendors are, right? Controller vendors, other flash vendors. Pick it up, start working with it, go make something awesome, and tell us what it is you've done with the project. I'm really excited to see what's going to be coming in the future. Softwareenabledflash.org. Again, please go join the mailing list. Really, thank you everybody for showing up, for listening to me. I hope you guys all have a great show for the rest of the week, and thank you.